The equipment in question draws a total of 37 amps, which exceeds the capacity of the number tensile cord and 30 amp twist lock. According to the National Electrical Code, the ampacity, that is the current carrying capacity of a number tensile cord, is 30 amps, and the maximum amperage rating of a 30 amp twist lock is also 30 amps. Exceeding the ampacity of electrical equipment can lead to overheating, insulation damage, and potential fire hazards. The manufacturer claims that the devices on the equipment do not all operate simultaneously, reducing the overall amperage draw below 30 amps. However, the NEC requires that electrical equipment be installed in accordance with its rated capacity. This means that the cord and plug used must be rated for the maximum amperage draw of the equipment. In this case, the maximum amperage draw of the equipment is 37 amps, which exceeds the ampacity of the number tensile cord and 30 amp twist lock. It is recommended to replace the number tensile cord with the number 8-so cord, which has an ampacity of 40 amps. Replace the 30 amp twist lock with a 50 amp twist lock, which has an ampacity of 50 amps. Ensure that the circuit supplying power to the equipment is rated for a minimum of 50 amps. While the manufacturer may have encountered situations where using a number tensile cord and 30 amp twist lock with equipment drawing up to 37 amps has not caused any problems, this is not in accordance with the NEC and is not considered a safe practice. To ensure the safety of the equipment and the building, it is recommended to upgrade the cord, plug, and circuit to match the equipment's maximum amperage draw. Therefore, several factors are important to consider. Firstly, the conductor ampacity is the maximum current in amps that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. Secondly, the National Electrical Code, or NEC, provides tables and guidelines for determining the appropriate conductor size based on the ampacity and other factors. These tables take into account the type of insulation, the ambient temperature, and the number of conductors in a raceway or cable. Thirdly, the NEC specifies that conductors must be protected against overcurrent in accordance with their ampacities. This means that the overcurrent protection device, such as a circuit breaker or fuse, must be sized to protect the conductor from overheating and potential damage. Number 10 AWG copper wire with Type 2W insulation has an ampacity of 30 amps at 60 degrees Celsius according to NEC Table 310.16. Number 8 AWG copper wire with Type TW insulation has an ampacity of 40 amps at 60 degrees Celsius according to NEC Table 310.16. The ampacity of a conductor depends on several factors including the conductor material, the insulation type, the ambient temperature, and the installation method. Copper conductors generally have a higher ampacity than aluminum conductors for the same gauge size. The insulation type affects the conductor's ability to dissipate heat. Higher temperature rated insulation allows for higher ampacities. Higher ambient temperatures reduce the ampacity of a conductor. The NEC provides correction factors for adjusting ampacities based on ambient temperature. The way a conductor is installed, such as in a conduit, cable, or free air, also affects its ampacity. Conductors installed in free air have a higher ampacity than conductors installed in a conduit due to better heat dissipation. When selecting conductors for an electrical installation, it is essential to consider all of these factors to ensure that the conductors are properly sized and protected. Using undersized conductors can lead to overheating, insulation damage, and fire hazards. In this scenario, the equipment draws 37 amps, exceeding the 30 amp rating of the number tensile cord. The manufacturer's argument that the equipment's devices don't operate simultaneously is not a valid justification for using an undersized cord. The NEC requires that the cord and plug be rated for the equipment's maximum amperage draw. To comply with the NEC and ensure safety, the number tensile cord should be replaced with the number 8-so cord, which has an ampacity of 40 amps. The 30 amp twist lock should be replaced with a 50 amp twist lock, rated for 50 amps. The circuit supplying power to the equipment should be rated for a minimum of 50 amps. This ensures that the entire electrical system, including the cord, plug, and circuit, is capable of handling the equipment's maximum amperage draw without overheating or posing a safety hazard. Using the correct size and type of electrical components is critical for safety and code compliance. Always consult the NEC and a qualified electrician to determine the appropriate conductor sizes and overcurrent protection for any electrical installation. There are more detailed aspects to consider that go beyond a general overview. Firstly, ambient temperature correction. The ampacity values listed in NEC Table 310.16 are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature exceeds 30 degrees Celsius, a correction factor must be applied to reduce the ampacity of the conductor. The correction factors are listed in NEC Table 310.16. Secondly, termination temperature. Electrical equipment, such as circuit breakers, switches, and receptacles, are typically rated for maximum termination temperature of 60 degrees Celsius or 75 degrees Celsius. The conductor connected to the equipment must be rated for a temperature equal to or greater than the equipment's termination temperature. If the conductor's temperature rating is lower than the equipment's termination temperature, the conductor's ampacity must be reduced. Thirdly, voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, conductors should be sized large enough to carry the load current without excessive voltage drop. The formula for calculating voltage drop is voltage drop equals current times resistance. Fourthly, conduit fill. The NEC limits the number of conductors that can be installed in a conduit. The conduit fill requirements are specified in NEC Chapter 9, Table 1. Exceeding the conduit fill limits can cause conductors to overheat and damage the insulation. Fifthly, directing factors. When multiple conductors are installed in a raceway or cable, the ampacity of each conductor must be reduced to account for the increased heat generated by the conductors. The directing factors are specified in NEC Table 310.15 cone. Sixthly, harmonic currents. Harmonic currents are non-sinusoidal currents that can be generated by electronic equipment such as computers, variable frequency drives, and LED lighting. Harmonic currents can cause overheating of conductors and equipment, as well as other problems. To mitigate the effects of harmonic currents, conductors should be sized to carry the increased current, and harmonic filters should be installed. Seventhly, grounding and bonding. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock. Bonding ensures that all metal parts of an electrical system are at the same potential, reducing the risk of electrical shock. The NEC specifies the requirements for grounding and bonding in Article 250. Eighthly, surge protection. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning, utility switching, and other events. SPD should be installed at the service entrance and at sensitive electronic equipment. The NEC specifies the requirements for surge protection in Article 280. Ninthly, safety interlocks. Safety interlocks are devices that prevent equipment from operating if certain conditions are not met. For example, a safety interlock might prevent a machine from starting if the guard is not in place. Safety interlocks are an important part of machine safety. Tenthly, labeling. Electrical equipment should be properly labeled to identify its voltage, current, and other important information. Labeling helps to ensure that equipment is used safely and correctly. The NEC specifies the requirements for labeling in Article 110. In Florida, where this equipment is located, there may be additional state or local electrical codes that apply. It is essential to check with the local building department or electrical inspector to determine if there are any additional requirements. Firstly, Florida Building Code. The Florida Building Code is based on the International Building Code, with Florida-specific amendments. The Florida Building Code includes requirements for electrical installations, including conductor sizing, overcurrent protection, grounding, and bonding. Secondly, Florida Electrical Code. The Florida Electrical Code is based on the National Electrical Code with Florida-specific amendments. The Florida Electrical Code includes requirements for all aspects of electrical installations, including conductor sizing, overcurrent protection, grounding, bonding, wiring methods, and equipment. Thirdly, local amendments. Many local jurisdictions in Florida have their own amendments to the Florida Building Code and the Florida Electrical Code. These amendments may include additional requirements for electrical installations. Fourthly, permitting and inspections. Electrical work in Florida typically requires a permit from the local building department. The building department will inspect the work to ensure that it complies with the Florida Building Code and the Florida Electrical Code. Fifthly, licensing. The electrical contractors in Florida must be licensed by the Florida Department of Business and Professional Regulation. Licensed electrical contractors have the knowledge and experience to perform electrical work safely and correctly. Sixthly, continuing education. Licensed electrical contractors in Florida are required to complete continuing education courses to stay up to date on the latest electrical codes and technologies. Seventhly, enforcement. The Florida Department of Business and Professional Regulation and local building departments are responsible for enforcing the Florida Building Code and the Florida Electrical Code. Violations of these codes can result in fines, penalties, and even revocation of licenses. Eighthly, resources. The Florida Department of Business and Professional Regulation and local building departments provide resources for electrical contractors and homeowners, including information on electrical codes, permitting requirements, and licensing. Ninthly, safety. Electrical safety is a top priority in Florida. The Florida Electrical Code and the Florida Building Code are designed to protect people and property from electrical hazards. Tenthly, best practices. In addition to complying with the Florida Electrical Code and the Florida Building Code, electrical contractors should follow best practices for electrical installations. These best practices can help to ensure that electrical systems are safe, reliable, and efficient. Therefore, the appropriate action is to replace the undersized cord and plug with properly rated components. Using a number 8 cord and a 50 amp twist lock ensures that the equipment is safe to operate and complies with electrical codes. It is essential to remember that electrical codes are in place to protect people and property from electrical hazards. Ignoring these codes can have serious consequences. The National Electrical Code, or NEC, is a comprehensive set of standards for electrical installations. It is updated every 3 years by the National Fire Protection Association, or NFPA. The NEC is widely adopted in the United States and is used as a basis for many state and local electrical codes. Firstly, scope. The NEC covers all aspects of electrical installations, including wiring methods, overcurrent protection, grounding, bonding, and equipment. Secondly, organization. The NEC is organized into chapters, articles, and sections. Chapters cover broad topics such as wiring and protection. Articles cover specific topics within a chapter, such as grounding and bonding. Sections cover specific requirements within an article, such as the size of grounding conductors. Thirdly, mandatory rules. The NEC contains many mandatory rules, which are identified by the word shall. These rules must be followed to comply with the NEC. Fourthly, permissive rules. The NEC also contains some permissive rules, which are identified by the word shall be permitted. These rules allow for alternative methods of installation that are equally safe and effective. Fifthly, explanatory material. The NEC includes explanatory material to help users understand the intent of the rules. This material is not part of the code itself, but it can be helpful in interpreting the rules. Sixthly, tables and figures. The NEC includes many tables and figures that provide information on conductor ampacities, conduit fill, and other important topics. Seventhly, definitions. The NEC includes a glossary of definitions for terms used in the code. Eighthly, enforcement. The NEC is enforced by local building departments and electrical inspectors. Ninthly, updates. The NEC is updated every 3 years to reflect changes in technology and best practices. 10thly, adoption. The NEC is adopted by many state and local jurisdictions in the United States. When adopting the NEC, jurisdictions may make amendments to the code to reflect local conditions.